Okay, so today's lecture is on weathering. These lectures in this unit are largely based out of lectures provided by the book, so the diagrams are very similar to the diagrams that are in the book, and I'll be explaining those in these series of lectures while I'm going through the PowerPoints. So this first lecture is on weathering. Weathering is the disintegration and decomposition of material at or near the surface. So weathering is the breakdown of rock. Now this is very likely to show up on the test, okay? I'm going to ask you what's the difference between weathering and erosion. And the big key here is that weathering is the breakdown of rock versus erosion. Erosion is the incorporation and transportation of materials by a mobile agent, usually water, wind, or ice. Short story for that, that's how it's described in the book, is erosion is the movement of rock. So weathering is the breakdown of rock getting broken apart. Erosion is the movement of rock. Mass wasting is the transfer of rock material downslope under the movement of gravity. Once again, that's the definition provided by your book. All I'm concerned with is that you understand that rock material is moving downwards. I think we all understand that that's probably due to gravity that's making things fall down. But this is a very long way of saying that rocks break apart, that's weathering, and then they get moved, that's erosion, and they also, when they move, they have a tendency to fall down, and that's mass wasting. Now there are two major types of weathering, mechanical and chemical weathering. Mechanical weathering is when rocks are broken down into smaller pieces by mechanical means. There's no chemical means involved. Chemical weathering is the chemical transformation of rock. So a reaction, for example, of acid and limestone would be an example of chemical weathering, whereas mechanical weathering is basically forcing rock apart. And we'll talk about some examples, but it can happen by ice, it can happen by salt. Basically anything that falls into cracks and pushes the rock apart will count as mechanical weathering. Now it's important to realize these two don't happen separately from one another. Chemical weathering helps mechanical weathering, mechanical weathering helps chemical weathering helps mechanical weathering, and mechanical weathering helps chemical weathering. So let's take look at an example where mechanical weathering, breaking apart rock, works to help aid chemical weathering. So this is a diagram that's in your book, and it can look a little confusing to some people, like what are they going on here, what's the purpose here of talking about these square units. So this is an analogy, a good analogy for this is thinking about putting sugar in your coffee. If you put sugar in your coffee with big granules or a cube, is that going to dissolve more or less quickly than powdered sugar? Well, powdered sugar, because it's broken down really small, will dissolve almost instantaneously in coffee, whereas a big sugar cube is going to take longer to dissolve. So this is basically what's going on and how physical weathering can help chemical weathering. Chemical weathering acts on the surface of a material. So the more surface area there is, the faster chemical weathering can occur. So in this particular example, they have a 4-unit square block that they break into smaller and smaller pieces. And as you break it into smaller and smaller chunks, you have larger surface area. What does that mean for chemical weathering? Well, it's just like the sugar. A big chunk of sugar will dissolve, or a chunk of rock candy in your coffee will dissolve very slowly. But powdered sugar, which is ground really small, dissolves very quickly. Now you need to know these mechanical weathering processes, and other than sheeting, you'll need to be able to identify them in your scavenger hunt. So the first one is frost wedging. Frost wedging is when water seeps into cracks and expands, and we'll get more into that when we look at a diagram. Salt crystal growth is very similar to frost wedging. What happens is as the salt crystal grows, it gets bigger and then once again pops apart the crack. Sheeting generates onion-like layers and exfoliation down. So what we're talking about here is the rock actually peeling apart due to, for example, a decrease in pressure. And biological activity. Well, the best example of that is another example of wedging. Root wedging happens just like frost wedging. And once again, we'll talk about that a little more when we look at the next diagram. So frost wedging. Ice takes up the same, if you start with, for example, a liter of water and you freeze it, you won't end up with a liter of ice. You'll actually end up with 1.1 liters of ice. That's because water expands when it freezes. Well, what happens in nature is that water seeps into the cracks, and when the water gets down into the cracks and suddenly the temperature drops below freezing, that water expands, pushes out, and breaks apart the rock. Now, if you live in the North Country, you've seen this. You've had to, if you own a house in the North Country, you've definitely dealt with this, or driven down a road in the North Country, because this is one of the dominant mechanisms by which things like potholes form or sidewalks crack. What happens is that when it's warm and rainy, water seeps in, or when snow melts, water seeps into the cracks. Then when the water freezes, it forces the crack apart, and that pops open the sidewalk. That's a big hint for the scavenger hunt. This is very similar to also root wedging. So the process of frost wedging is very similar to root wedging. What happens in root wedging is you have a little skinny root that gets into a crack, and then when the plant takes up water, that root expands and it pushes apart the crack, and that once again pops apart the rock. Now you see that all the time. If you've ever seen grass growing in a sidewalk or dandelions, that's why it's important to go across your sidewalk and pull those out, because what they're doing is that they're widening the cracks. They're not just living there, they're taking an active role in breaking apart the sidewalk. So sheeting and exfoliation is something you're only going to see in actual rock. This is something that doesn't really happen to man-made objects. So sheeting, also known as, sometimes it's called weathering due to unloading. What happens is you end up with a pluton that's under pressure. So that's a big igneous rock. It's under pressure because it's buried. And then when the rock over the top of it gets removed, that causes the pluton to expand. And that expansion causes cracks. Okay, so you're relieving, when it's tight under pressure, it doesn't have any cracks in it. But once you release that pressure, it expands, and the expansion forms cracks. And that's what drives sheeting and exfoliation. Now, chemical weathering is another type of weathering you're going to have to find on your scavenger hunt. Chemical weathering occurs when you have a chemical reaction occurring, such as oxygen or carbon dioxide in the form of carbonic acid reacting with the materials. So when oxygen dissolved in water, particularly slightly salty water, comes into contact with anything that contains a metal, it oxidizes. And this is something you see all the time. If you've ever seen red on a building or on a car, that's rust, and that rust is a form of oxidation. Also, if you've ever seen really old pennies used to be made out of copper. And copper, when that oxidizes, it turns green. A great example of really big, really cool oxidation is the Statue of Liberty. The Statue of Liberty is made out of copper, and her surface has been exposed to air and water for a long period of time. That air has oxygen in it, and when that dissolved oxygen contacts the Statue of Liberty, it oxidizes, and that oxidation turns the Statue of Liberty green. Carbon dioxide dissolved in water and carbonic acid. Carbon dioxide dissolved in water forms carbonic acid. So at some point we're going to talk about acid rain, which is a bad thing. But rain is naturally acidic. Rain becomes acidic because our air contains carbon dioxide. This just happens. This happened long before humans existed. Humans are making it worse by making the water more acidic in the rain, but the rain itself is always acidic. acidic water can dissolve certain types of rock, particularly limestones. Limestones dissolve, and marbles. Limestones and marbles dissolve really easily in the presence of acids. So this is a really good example of that the rock type changes what type of weathering we're going to see. And in this case, we're looking at dissolution. So on the left-hand side, you have granite. Granite is a rock that is not susceptible to, or not very susceptible to acid dissolution. So because it's not susceptible to acid dissolution, rainwater, slightly acidic rainwater, has no influence on the tombstone. But if you look at the tombstone to the right, that tombstone has had its name completely obliterated, and that's because this tombstone is made out of marble. Marble and limestone are both made out of calcite, and that means they dissolve really easily in the presence of acid rain. Now, that means a lot for certain important monuments. So, for example, the Taj Mahal is susceptible to chemical weathering through acid dissolution simply because it's completely made out of marble, so it dissolves rather easily. Other important factors for influencing the rate of chemical weathering. One big one is climate. Chemical weathering loves places where it is warm and where it is wet. Where it's dry and cold, there can't be a lot of chemical weathering. Why? Well, first of all, most types of chemical weathering absolutely require the presence of water. So, for example, if you never get your tools wet, they'll never really rust, okay? If you get them wet either with the oils in your hand or with the moisture in the oils in your hand, or you leave them out in the rain, then you'll see them rust. But if your tools are always protected inside, even if they're exposed to oxygen, they don't rust. Why? Because you need water to be a carrier to hold that oxygen right next to that metallic surface in order for oxidation to occur. Similarly, you need water to dissolve the carbon dioxide to turn it into carbonic acid for acid dissolution to occur. So for chemical weathering to really happen, you need water. And then warmth. Warmth helps speed up chemical reactions. Now it's a little bit different for physical weathering. For physical weathering, cold and warm cycles help a lot. The reason for that is if we're going to have something like frost wedging occur, we need those melting and those thawing and those freezing cycles to help break apart the rock. We also need the presence of water to help, for one thing, bring the dissolved salts into the cracks where they can reprecipitate, form new salt crystals, and force it apart in salt wedging. In root wedging, we need it to support the life of the plants. And in frost wedging, we need water just to make ice. So chemical weathering tends to be most effective and sped up in warm temperatures with lots of moisture. So that means you're going to see that a lot in the rainforest. Whereas physical weathering likes lots of water as well, but it tends to like temperate zones where there's lots of cycling between hot and cold to help really drive that frost wedging. So in a place like Watertown, where we're a temperate climate, we're going to see a lot of physical weathering. Now, differential weathering. Differential weathering is caused by differences in the composition of the rock. So you get uneven weathering patterns. So you'll have portions jutting out. If you look at this example right here in the western United States, you can see some of the rocks have portions that are sticking out and some that are sticking in. That actually has to do with the different weathering properties of the different layers of rock. Now, when we get into how sedimentary rocks form, we'll talk a little bit more of how one rock that's like this has different properties in layers, because that's how sedimentary rock forms, is in layers. So you tend to see a lot of differential weathering in sedimentary rock. It's also how you find fossils. Fossils are very often harder than the surrounding bedrock. So what happens is that the surrounding bedrock weathers away and the fossil's just sticking straight out. So that's it for the basics of weathering. This is the most important points in weathering that you will need for the upcoming exam.